Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It's my great pleasure to welcome ARKADIUSZ BOCHNIAK, who used to be from Kraków, and he changed Kraków for München, right?
Yes.
And he will tell us how quantum twins occur in quantum optics. Just kidding. It's about Mycielski construction and quantum twins. It's all yours, take it.
Okay, thank you. Yes, so as announced, I will talk about the Mycielski construction, its quantum version, and how the study of this construction led us to the concept of quantum twins and the properties of those objects. So, but first I will start from very down-to-earth introduction. I will try to motivate the concepts I'm using. I would like to say why those objects or those type of tools are interesting and important in different branches of science. So let me just start with some very, let's say, easy to accept statement that the graph theory is a useful tool not only for mathematics itself, but also has a lot of applications in, for example, computer science, chemistry, physics, or many other things like, for example, even sociological sciences. But for us, the main place where we would like to work with the graphs are physics and information theory, and those are the sciences from which I would like to bring some motivations for what I am doing here. So let me just start from like the first example where the graphs appear in quantum information. So let's consider two persons. Let's call them, as usually, Alice and Bob. And let us assume that Alice would like to communicate something to Bob. So we are saying that Alice and Bob share some classical communication channel. So it means that there are like two finite sets, one associated to Alice, the other to Bob. And there's a map that tells us about what is the conditional probability that Bob receives value B from the set B if Alice had sent value A from the set A, if the channel is not perfect, meaning there is some noise that can appear through the communication. So this is the scenario we are considering here. And to such a channel, one can associate certain graphs. And then by studying those graphs, we can say something about the channels. So what is the first graph one can associate? Is the so-called distinguishability graph. So the elements of the set A are the vertices of this graph. And we are connecting two such vertices if basically those two inputs in the channel can be distinguished by the channel. So the noise didn't influence the fact that we had the A1 or A2, right? And this can be written formally in this way, like here, that the product of those two values is 0. And
just a quick question: probe stands for
probabilities. Probabilities.
Okay, so probe
should be probe.
Probably should be probe.
Sorry, yes, not the probe. Okay, the
Okay.
type. Okay. Yeah. Right. Yep. Yeah. Okay. Sure. Yeah. And okay. So having this graph, we can also consider the complementary one, which is called the confusability graph. So basically, it tells us how much information we lose because of the noise. So this is the way you can characterize the channel by studying the properties of this graph. And basically, if the confusability graph has, the intuition is that if the confusability graph has a lot of edges, basically it means that there's a lot of noise in the channel, so you can lose a lot of information. That's the intuition. And those concepts were studied in those two papers I'm citing here. But okay, this is the classical channel. So what can happen if we are looking at real world, where we are assuming that the real world is described rather by, it's described by quantum mechanics, not classical mechanics. So basically, you would like to know how to transfer quantum information. So the simplest example is that we have a system described by some density matrix, and we would like to know how it changes in time. So we have a description of time evolution of this quantum system. This is like the simplest example of quantum communication channel. More formally, we have two Hilbert spaces, and the quantum channel is just a linear CPTV map between the corresponding algebras.
Sorry, I presume CP is completely positive. What is TP?
Trace preserving.
Okay.
So we have completely positive trace preserving map between the binary algebras of trace class operators on those two Hilbert spaces. So this is the definition of quantum channel, which is widely used in the literature, but also one can consider the adjoint of this map, which will be a UCP map. And
Wait, which again, which is what? CP is completely positive. What is U?
unital.
Unitary, okay.
And
So
sorry,
preserve the
I'm a little bit worried about this Banach algebra stuff. Trace class operators form a Banach algebra. Probably Banach space, yes.
Banach space. Oh,
Space
yes,
would be
sorry.
more safe to say. Mhm.
Yes, it's a Banach space of trace class operators, right?
Okay.
The algebra, of course. And yeah, so basically, whenever we are talking about quantum channels, we either refer to one description or the other. So in the literature, basically, people are using this, the name quantum channel for those two maps. And from the context, you basically know which one we are referring to. But the second one is actually something that is more closer to the sister algebraic description of quantum world, because we are working now with the maps between basically sister algebras, algebras of bounded operators. And this is the way we can now think about quantum channels in the non-commutative world. So this is like the concept that will be useful for us. So how we can...
Sorry, I have a question.
Yes.
Could you come back to this slide? Could you compare this notion of the quantum channel to the notion of the classical channel?
Basically, you have to reverse the arrows. The thinking. It's so if you have if you consider the classical spaces.
So sorry. Maybe I will explain what I would expect from this explanation, because I see that in the classical situation, on the left-hand side, you would have some atomic measures, probabilistic atomic measures, and arbitrary probabilistic measures on the right-hand side.
Yes.
And now you are replacing both sides by density matrices, essentially.
Yes.
Okay. So this is this generalization is more than only replacing these probabilistic measures by these density matrices. It is also replacing the domain, these atomic measures, okay, to arbitrary density matrices. So this means that you are not transferring some signal like pure state, obtaining some state on the right-hand side. You extend your channel also to transmitting
statistical ensemble,
basically. Are already quantum fuzzy in a sense.
Yes, so like the whole statistical ensemble. That's correct.
Am I understand? Do you understand it?
Yes, yes.
Okay.
Yes, I agree with this. Yeah.
Thank you. Thank you.
That's correct. Okay. Okay, so for that kind of definition of a quantum channel, if you are working with matrix algebras, there's a simple characterization of quantum channels. Basically, in order to study quantum channels, you have to study the so-called cross operators, which are used by choice theorem to write the form of this channel. So as the UCP map from one matrix algebra into the other one. So basically, the theorem says that there exists a finite n bounded by the product of the dimensions, bounded by the product of the dimensions of those two algebras, and a set of cross operators labeled by, from 1 to this capital N, such that this map is of this form. And basically now you can form different types of operator spaces, operator systems from those chaos operators. And by studying properties of those objects, you can say something about the quantum channel. Okay, so that's the idea. And of course, we can also talk about the noisy quantum channels. And then you would like to have something like the analog of confusability graph for quantum channels. And this is the place where the quantum graphs appear in this story. So basically, the quantum graph is something that can be used to understand how much noise we have in the quantum channel. So that's the motivation. I mean, I'm not going to too much details here, just to show you the context. And now, what else we can say about the channels?
Sorry, I don't understand the word remedy here.
Oh, okay. So, okay, maybe it's the wrong word, but the point is that we are...
Remedy for what?
Where is it coming?
So quantum graphs.
So we...
What introducing quantum graphs?
Okay, so we need an object.
Or possible.
Oh, okay, so okay, it's just a question if there exists an object that can be used as a classical graph to say something about the noise in the channel, but in the quantum setting. So is there like a natural candidate for this thing? And the choice you can make is like by defining this object, which is called a quantum graph. And then by studying the quantum graph, you can basically say something about the noise in quantum channel. So that's the idea. So
makes sense.
Maybe the word remedy is not the best one here, but it's for this kind of, maybe not issue, but this kind of question you have. If there exists an object that tells you about the noise in the quantum channel.
So is it the problem that in the presence of noise, the confusability graph cannot be even defined? Is it the problem?
No, but because for the quantum channel, we don't have a notion of confusability graph. For the classical channels, we can say about what is the confusability graph. This is a well-defined object. For the quantum channel, this object is not well-defined because it's ill-defined. Yes, because the problem is that
for a problem which could be removed. Remedy quantum graph. Remedy.
Yeah, because I mean, in the quantum setting, we don't have the finite set at the beginning for which we can form the set of vertices, right? So we need like a quantum analog of the finite set of objects. And the solution can be constructed by using quantum graphs. So the quantum graph is like an analog of confusability. I mean, it can be understood like an analog of confusability graph for quantum channels. Okay. But where else we can use channels, graphs in information theory? So now imagine a situation that, okay, in addition to the two players, to the two persons, Alice and Bob, there's a third one that's called Charlie, and let's associate with him some finite set C. And then we can imagine the following scenario that Alice and Bob are now players. They would like to play against the Charlie, which is referee here. So the scenario we have is the following. So Charlie is choosing some value from his set, let's say little c, and using some conditional probability, he decides to send some message x from a finite set x to Alice and some element u from a set b to Bob. And suppose that Alice was equipped with some function between the set x and set a. And using this function, she can produce a value a, a value of x. And then she can send this value to Bob using the channel phi. And of course, the channel was noisy, so Bob will receive some value b. And the goal of Alice and Bob is to determine which value c was chosen by Charlie. And now it turns out that this problem can be described by introducing another graph, which is so-called characteristic graph of the channel. I will not going to describe how it is defined, but basically we are using the set x as a set of vertices, and you can define a rule for the edges by using the properties of function p. So the conditional probability p can be used to define a set of rules how to define the edges on the set x. And it turns out that the existing of the winning strategy for this kind of game exists, even only if there exists of homomorphism between the characteristic graph and the distinguishability one. And this problem was discussed in this paper here. So actually you see that some properties of some object can be encoded by saying that there exists a strategy for some game, a winning strategy for some game. And this idea goes to the following idea that you can try to define some characteristics of, for example, graphs by saying that there exists a winning strategy of some non-local game. And of course, you can now think about what happens if the players now are using quantum channels to communicate. So then you can think about how those characteristics can be defined for quantum graphs. But also you can imagine a situation where the players are not completely independent. I will discuss it in a minute, what does it mean, but they can be non-trivially entangled. So that this notion will be explained in a minute. So this is just to state the problem. And let
I have a
me...
question again. Sorry,
Yeah.
I have a question. Up to now, there was nothing related to locality or non-locality. You had only this completely positive map. Okay.
Yeah, exactly. So nothing about
this locality or non-locality.
So it will appear in the So it will appear in the next slide. So I will go to this, okay? Because this is exactly the thing I have on the next slide with the more rigorous definition of what I mean by all those words here, okay? Because this is very compact, very compressed definition here. I mean, these are just the words. So let me go to this slide and I will give you a definition in a second. So before the definition, I need to give you the classical example where we are not talking about the quantum system. So there's no entanglement, nothing about the locality. So we have now the following situation. So suppose that now the Charlie chooses two vertices. Let's call them V and W from some graph G. And he's going to send one of them to Alice and the other one to Bob. And now Alice and Bob have to respond with some values alpha and beta from 1 to C according to some set of rules, okay? So basically, if the vertices are the same, they have to say that alpha is equal to beta to win. And then if the two vertices form an edge, they have to give different values alpha or beta. And the statement here is that the winning strategy of this kind of game exists if C is at least the chromatic number of G. So in other words, the chromatic number of the graph can be defined as the minimal value C for which there exists a winning strategy of this kind of game. And now, what is the quantum version of that, where this non-locality thing and entanglement will appear? So basically...
I have a stupid question.
Yeah.
I'm looking at this curly braces, V comma W, edge implies alpha not equal to beta.
Oh,
Why
so this is
not
like
just write V be distinct from W? There is an edge.
Yeah, there is an edge, exactly. So
there must be an edge between them. Okay.
yes, so by the curly bracket, I mean an edge between two vertices.
Edges are pairs of elements.
Yeah, so edges is not a pair.
But not every pair has an edge.
No. Just a rule of winning the game. So we are specifying when the players are going to win the game, and those are the rules they have to satisfy. Those are the rules of the game. So if V and W form an edge, the requirement is that the players have to give different answers in this game.
But if there is no edge, there is no implication.
Exactly. Yes.
Okay. Yeah, thank you.
Okay. So now what is the quantum version of this? And this was discussed in this paper here, where this notion, this quantum version of this chromatic number was defined for the first time. So basically now, as always, almost always in quantum mechanics, people are considering not giving a value alpha or beta from some finite set, maybe with some probability, but now saying that this value is obtained by performing some kind of quantum measurement. So what does it mean is that the players are now modeled by some set of positive operator valued measures. So we have some sets of operators E and F here. And now those rules can be replaced by the quantum analogs. So there exists some state psi, and this is the thing that is this entanglement between the players. So basically, we are saying that to the players we can associate some Hilbert spaces, right? We can consider the Hilbert space now on which those operators will act. So this must be defined a priori, right? So we're defining the Hilbert space, so we're defining some state on this Hilbert space. And this this state may be entangled or not. And then we are computing the expectation values of those operators in this state. Okay, so this is the quantum version of those rules here. And the fact that the players are entangled or not is about the entanglement of the state here.
I have a question. Is it crucial that psi is a pure state?
No, it cannot. Well, actually, it must be entangled to have something non-trivial here.
So it is enough? I mean, the existence of this pure state can be
Well,
the
okay,
definition
so,
of the quantum chromatic number. This state be replaced by a non-pure state.
actually, okay, so there's one theorem in the paper here that they're saying that actually you can choose any entangled state. So that doesn't matter which one you're choosing. Not pure one. So any entangled state, that's fine.
Any state,
Yeah, basically, any entangled, yeah.
not necessarily pure.
Yes, exactly.
Okay, thank you.
Yeah, okay. And then you can, okay, ask the same thing, the same question as here, right? You can ask, what is the minimal number such that the winning strategy exists, right? And you can answer. And you can define this number to be the quantum chromatic number, just by complete analogy to what happened in the classical scenario. Okay. And of course, this concept now can be extended to quantum graphs, because I mean, we have Hilbert space, we have some operator algebras, whatever. So we can just try to do this for purely quantum graphs also. And this is also done and known in the literature. Okay. So as I said, those are like the main tools that somehow are useful for us. And also those problems motivate what we are trying to do. And one thing is that we know that there are several classical characteristics of graphs, several classical properties of graphs that can have quantum analogs, and the quantum analogs might give some non-trivial, may have some non-trivial properties. So, for example, here in this case, it may happen that the fact that the two players are quantum, I mean, meaning they share the quantum state, can have the so it will imply that this number here is small. So basically, there's some kind of quantum advantage here. So basically, sharing the quantum state can mean that you need less number of colons to perform the colony in this quantum way of thinking. So basically, the quantum analogs might have some non-trivial properties, the property that you don't expect at the very beginning, and it's natural now to ask about different problems in graph theory, and to ask what are the quantum analogs the quantum analogs of those problems, of those objects in the quantum world, and what is the effect of having this non-commutativity here. So the problem we are looking at is the following. So there is a well-known problem in graph theory.
Sorry, forgive me once more. If I understand, these rules allow you to speak about the quantum chromatic number of a classical graph.
Yes, but this can be also extended to quantum graph, but it's different definition. So, I mean, I'm not saying that those rules, exactly this kind of descriptions for the quantum graph. I'm saying that this kind of gain can be also extended to quantum graphs, but it's more involved outside this.
But I don't understand the analogy between these rules for classical graphs and vertices and classical responses. Now they are indices.
Yes.
Indexing what? POPMs.
Positive operator valued measures.
Yeah.
So we have a.
So it's a matrix.
Yeah, it's an operator.
EV alpha is an entry of a matrix.
Well, you can think
What
it
is
this way,
this?
but this is it's a set of operators, basically. It's a family of operators indexed by two indices.
Okay, they are indexed by vertices of the graph and the responses.
Yes, exactly.
Mhm. Okay. Okay, thank you.
And they must be positive. I mean, there are like set of conditions that this family must satisfy to be a positive operator valued measure of this on this Hilbert space. So this is okay. I didn't write the full conditions here, but there's like a set of conditions that E and F must satisfy in order to be P of EMs. Okay. And for example, this the first rule here is like I mean, it's easy to say this is an equivalent of the analog of the first one, right? That if the two vertices are the same, we are demanding that for different alphas, this expectation value must be 0. So the result of the measurement in this case is 0. So we don't expect to have the same colors associated to the same vertices. That's the intuition. Okay. But let me go now to the main problem I would like to discuss in this talk. So I would like to look at the classical problem, which is known since 50s, even earlier, in graph theory. And the question was that does there exist a graph which is triangle-free, meaning that there is no closed triangle inside the graph, and such that this graph has an arbitrary large chromatic number. So can we always, for a given number n, construct a graph which doesn't contain any triangle, and the chromatic number of this graph is equal to n? And the solution was found by Mycielski in 55, and basically it can be summarized that for a given graph G, there exists a larger one, which is called the Mycielskian of G, such that we don't change the clique number. I will explain all the notions in a second, and I will also give you the precise description of this construction. And moreover, that the chromatic number of the larger graph is larger by 1 from the original one. And now if you have a graph G to be just a complete graph of two vertices, and you repeat the construction sufficiently many times, you can get any chromatic number, but you will not produce any triangle from this construction. So basically, this is the answer for this question. And what we would like to do, we'd like to look at the quantum version of this question, and we would like to study how this kind of transformation affects all the characteristics of the graphs, or the quantum characteristics of the graphs, which can be defined through those, for example, non-local games. And
sorry,
also,
I have a silly question.
Yeah?
What was the reason of Mycielski's dislike of triangles?
to be honest, I don't know. I mean, I know that this was like a quite famous question at the time, but I don't know why the lack of triangles was.
If you tell me no loops, no, closed paths, I understand. But
I mean,
why
in a sense, it's a bit
triangles?
counterintuitive that you can. It's a bit counterintuitive that you can enlarge the chromatic number. I mean, to an arbitrary one, but you don't produce any closed triangle inside this. I mean, that was the explanation I found in the paper. That basically it's a bit counterintuitive that you can do that. And yeah.
So pentagons are fine, right? Just triangles.
Yeah, triangles. But this construction also tells you that if there was no pentagon inside, you cannot produce one. You cannot enlarge the. Okay, no pentagon. Okay. No, just forget about what I said about pentagon. Okay, it's about the triangles here. This is about the triangles, and this can be generalized to any complete graphs, basically. So if there was a complete graph, if there was no complete graph of n vertices inside, you will not produce a new graph with some complete graph using this construction. So yeah, so it's not only about the triangles, about any complete graphs inside the original graph. Okay. So having said that, let me just go to the main part of my talk. So in the first, as I said, the first part was just to give you some motivation, some overview of concept that led us to this problem. And now I'm going to give you the more precise description of what we are doing. So first, I will describe what the classical Mycielski transformation was, and what were the classical generalizations known in the literature of graph theory. So how different ways of generalizing the Mycielski transformation was discussed. Next, I will give you a brief overview of quantum graphs, so just saying what this object is and what kind of properties it has. And after establishing the language, I mean, having the notions fixed, I will show you how we construct, or how we propose to construct the Mycielski transformation for quantum graphs, and what are and how this construction changes the quantum characteristics of the original quantum graph. And the final part of my talk will be dedicated to the symmetries or quantum symmetries of graphs and the Mycielskians, and the study of quantum symmetries of quantum Mycielski graph. The study of those quantum symmetries of Mycielski basically will lead us to the concept of quantum twins. And after that, I will show you some properties of those objects, and finally give you some summary of open questions and what we are working so far. Okay, so let me start with the definition of some basic objects that we are going to use. So we already used the notation, but let me just summarize it here. So for an undirected graph G, V with index G will denote the set of vertices, EG is the set of edges, AG will denote the adjacency matrix of the graph, and by chi of G we understand the chromatic number, which is the minimal number of colors that could be used to label vertices such that no edge has two endpoints of the same color, and the omega of G is the so-called clique number, and as I said, it is the size of the largest complete graph you can embed in G. Okay. What now, having those notions, let me show you what the Mycielski transformation was, and I will give you an example how it works in practice. So basically, the idea is to enlarge the original graph by adding the second copy of it and some distinguished vertex denoted here by this black dot. And the edges of this new graph are now described by this adjacency matrix. So basically what we are doing, we are connecting the second copy of the graph with the distinguished vertex. So this is the set of ones in this, sorry, there shouldn't be transposed here. The set of ones in this place in the matrix and here. We don't change anything in the original graph. And whenever there was an edge between two vertices in the original graph, let's say between V1 and V2, then we are connecting. Let me see this on this. Let me show this on this example. So there was an edge between V1 and V2 here in the 0 level. Then in the first level, we are connecting V1 with the copy of V2 because there was an edge on this level. The same thing for this edge here. So whenever there was an edge here, we are connecting this vertex with the copy of the second one. And we are doing this for all pair of vertices in this graph. Okay, so
wait. So and how about if it's the other way around? Sorry, this is a copy. Sorry, no, I take it back.
It's the second copy.
Yeah.
Okay. And the point is that there's no vertex.
But wait, I'm confused. If it's just a copy, right? Wait.
Copy of vertices.
Vertices.
Yeah, exactly. This is we are copying the set VG. So the set of vertices in the new graph is the original one plus the copy of the original one plus the distinguished vertex.
Yeah. But I try to understand this adjacency matrix. I'm trying to understand edges. So now I think my second copy of the set of vertices, and you are saying is that I'm not putting any edges in between them, right?
Exactly. We are connecting only to the distinguished one or in cross, like with the first copy.
Okay, thank you.
Okay. And then in the paper, Mycielski have shown that if the graph G was irreflexive, so there was no loops, then this construction doesn't change the doesn't change the Clique number. So omega of mu of g is omega of g, but the chromatic number is larger by 1. So this is the classical.
Sorry, can you say again what you mean by irreflexive?
You don't have an edge from V to V.
You don't have what? Edge?
Edge from V to
Wait,
V.
let me switch off the air conditioning. Wait. Okay, sorry, because of a noise, the humming of air conditioning, and in Warsaw it's plus 27 or something.
Okay.
So I have problems understanding what you are saying. Please try again.
Yeah, I just said that it means that there's no edge from vertex V to itself.
Aha. From
Adjacency matrix
so no
has
loops,
zeros
okay.
on the main diagonal.
Okay.
So this notion is different from the opposite to reflexive in the context of directed graphs.
Okay.
Different. It's like the equivalence relation, reflexivity. Reflexivity
So
means
for
that.
undirected graph, reflexivity means that there's a 1 on diagonal in the adjacency matrix. For undirected.
Mhm.
Okay. Fine. Yeah, so now let me give you some possible generalization of this construction, which is actually well studied. And you can, of course, now think of more copies of the original graph and try to do similar constructions. So basically, like adding, in this case, R copies, right, from 1 to R. The 0 one is the original one. And you are doing exactly the same construction between the layers. I mean, it's quite complex way of writing that, but actually it is what I wrote on the previous picture, on the previous diagram. So we're adding like the edges between the distinguished vertex and the last copy, and then you are doing inductivity reconstruction from the previous.
You cannot update it by iterating the usual Mycielski construction.
Yes, exactly. So the point is that if you have like I don't know, let's say A and B, then mu with index A composed with mu with index B is not mu with index A plus B. Or, yeah. So there's no like sum rule, whatever.
Okay. Yeah, it's clear. Sorry.
Okay.
Mm-hmm.
Fine. Okay, so this is the classical construction. And as I said, we would like to find the quantum analog of this construction.
Sorry, I have two questions. First of all, so the order matters in here, because if you are forming these pairs of vertices, first one is from I's copy, and the next one is from I plus first. Okay, so
yes.
Yeah, so this is not only, so it is not enough to say that the definition, okay, that it's a union, because there is an order on this construction. Second, what can be said about the chromatic number of these R iterated?
Okay, so this is something that I will discuss later, but the short answer is nothing. For R larger than, I mean, for this generalized construction, in general, nothing.
In this construction, what? Sorry?
In this construction, if R is general, so not necessarily correspond to the original Mycielski construction, you cannot say nothing about the about this schematic number. So it may change, may not. So there are kind of examples for this kind of. But okay, there is one thing I maybe should discuss it later, which is the so-called generalized Stibitz theorem, but it's more involved. I don't want to go in the details. I can maybe discuss later, but I don't have it here in this slides. But there is something that can be said in this context for generalized Mycielski transformation, but the way of formulating this theorem is more involved, and I don't want to do it without. I mean, I don't have nothing to write now, so I cannot just simply say it. But okay, there is something that can be said. Actually, yeah.
If I understand, so even in the classical situation, generalizing this Mycielski's construction, you are losing Mycielski's theorem.
Yes, that's correct. Okay. Yeah. Okay, and as I said, the main goal we had is to generalize it to quantum setting. So for that, I need to say what I mean by quantum graph. So I'm using the definition which you can find formulated in this way in the paper here. I mean, there are different equivalent definitions, but I'm just choosing one to like formulate the problem. So now the quantum graph is a triple, is some finite quantum space. And
Yeah, what exactly do you mean by this?
I mean,
okay. CG?
Yeah, just okay. So I'm saying okay. So there exists finite dimensional sister algebra C of V, but I'm calling the C of V C of G. So in other words, I have a finite dimensional sister algebra. That's all.
Okay. So also this V is not defined theoretically, it's just a symbol, yes?
It's just a symbol. Yes, of course.
Okay.
So what is defined is the sister algebra C of G, and I'm saying that C of G is the dual to V in this standard sense of noncommutative geometry.
Okay, that's
The functions on G.
Yeah, but why G not V?
Because okay, just to simplify the notation,
It's a quantum space. It's not the set of vertices.
No, I understand, but just to simplify the notation, because in a second I will have the GNS space corresponding to the pair V psi, and I should call it L2 of V psi, and I will have now this guy as the index of some operator, and it will be a mess of notation. So just to simplify everything, I'm just calling this G, carry G. So L2 of G, C of G, everything will be with this G. Because for example, here I have the identity on L2 of G. I should have identity of L2 of C of V, comma psi. And I wanted to avoid this kind of notation. So just to simplify the notation, nothing.
It does make sense, of course, because being a quantum graph is an additional structure on this algebra C of G. It's not C of G period. It's C of G equipped with some additional structure.
Right.
And all this triple together is G, and C of G is this algebra.
I missed this notation that G is the triple. Okay.
Yeah, just a triple. Exactly.
This state and this
yeah, I just wanted to avoid like using the triple all the time. Just this. Okay. Okay, so I have the finite quantum space. I have a faithful state, and then okay, I have the associated GNS space L2. And now both multiplication and unit in C of G can be represented as linear maps of this form, right? And the third assumption is that psi is a special in the sense that it's a so-called delta form, defining this way, so that M composed with M adjoint is some number squared times identity operator L2. So that's the definition of delta form. And A is a self-adjoint map on L2.
So sorry, delta is just a number?
Yes, just a positive number.
Okay, and I don't understand this condition. How does it refer to psi? Since it is about.
Okay, let me go to this. So L2 is a Hilbert space with an inner product defined by psi.
Okay.
In order to define the adjoint, I need to use psi.
So psi
the psi is involved in this definition.
Yes. Okay, and you consider the identity operator between this L2, which is constructed with the help of psi. Okay.
Exactly. Yes. Okay. And okay, those two conditions that A has to satisfy basically reflect some classical ones. So the first one is saying me, if A is an adjacency matrix of a classical graph with delta equal, the dimension of, the number of vertices basically, square root, depending on the converter. I don't remember the square root of or the number of vertices. Basically, the first condition means that the adjacency matrix has only zeros and ones. The second condition means that the matrix is symmetric. It's written now in this language, but this is like the analog of those classical properties. I'm not saying that this is like the best definition or whatever. It's just one of the possible definitions of quantum graph, and this is the one which is quite widely accepted. So we are using this just to fix some framework. And in this framework, the graph is called reflexive. The quantum graph is called reflexive if this equation is satisfied, and is irreflexive if this reference site is 0. Okay, so that's the definitions. So the set of definitions.
Sorry, is it automatic that we have the dichotomy between this reflexive and irreflexive?
Delta is positive by definition.
So the only possible values, condition for this delta is delta square is different from 0, or it is 0?
I mean, delta is always positive by definition. So psi is delta form of positive delta. Delta must be always positive. So
Always
it's a part of the
positive.
definition. Yes, it's a positive in the definition.
Yeah,
Yeah, but if I understand Tom's question correctly, you have on the left-hand side, you have the identical expressions. And
Yes.
now, is it obvious that they have to be, say, non-negative real numbers, and the only choice is between being positive or 0?
Yeah.
Can it be
Yeah.
that it's something negative or maybe not even a number?
Yes, not even a number, of course.
Okay, that I don't know. I don't know.
Because the
That's,
dichotomy would be is equal to 0 or different from 0.
Yeah.
Why
Okay.
it is scalar?
Exactly. That's exactly, yeah.
okay, that I
Is
don't know.
automatic consequence of this 3 and 4?
I don't know the answer right now. I can check this, but okay, I don't remember this, to be honest.
Okay, good.
But that's a good question. Yeah, I was not thinking about the dichotomy. Okay, but that's okay. That's the set of definitions. So we have the notion of quantum graph and the notion of reflexivity. Okay. And this, of course, I said, different way of defining quantum graph. And just to give you some brief overview of how it is done. So since C of G is finite dimensional, it's also for linear algebra. You can think about the commutative of C of G, and you can consider this map defined here. So we just have an X mapped to this nice expression, and you can show that this is a projection that satisfies those conditions for all T1, T2 from the commutant. And you can take the image of this, of the full space of operators under this map, and you can show that there is a self-adjoint operator subspace of bounded operators on L2. And moreover, you can also show that this is a bimodular over the commutant, and this is done in this paper. You can check this construction here. So what does it mean is basically that we have a triple. We have some algebra of bounded operators. We have some von Neumann algebra here, and we have a self-adjoint operator subspace of this B over 2, which is a bimodular of the commutant of C of G, of this von Neumann algebra. And this is actually the framework in which Rivers formulates his quantum graph. So the quantum graph of Weaver is a triple of a BL, BL2, some von Neumann algebra here, some self-adjoint operator subspace, which is a bicommutant over this, a bimodule over the commutant of this von Neumann algebra. So that's the connection between those two concepts. And for the classical graph, basically, you can easily compute this operator space. You just take the linear span of all matrix units, Eij, where Ij is the edge in the original graph. So the pair Ij from edge. And you can show that this is indeed the operator space that you can get from this construction. If you follow all the stuff. I mean, it's quite, it's straightforward, but requires some computations. I will not go into details, just wanted to mention that, there's at least one different definition of quantum graph, and under certain conditions they are equivalent, and you can find a way of going from one to the other. I am not going into details, you can find them here, for example. Okay.
Sorry, I lost my focus at some moment. Is it clear that these two approaches to quantum graphs are equivalent, this Weaver's triple and this triple you started with?
So this is what I said right now, so that under some assumptions, yes. And you can show that you can follow this kind of construction to go from the previous one to this one, and you can find the details here. I am not going to discuss the details and the proofs, but you can find the details here.
So this is the theorem of Ganesan.
Well, she's discussing this. I'm not sure that in the paper is like the first place where this appeared. So because there are some references to other papers by Mike Brennan from like a few years earlier, where some parts of this were discussed.
So who proved this equivalence of these two approaches?
I would say that in her paper there is a proof, and there's also a discussion in this paper. There's a more detailed discussion in this paper with some, because you can also relax some of those conditions. So I mean, in this paper you can find a lot of different versions of the formulation of quantum graphs and interplay between the different formulations. So I would recommend to look at this paper for like different type of formulations of quantum graphs and what you can, do if you are not assuming something or what you cannot do. So this is like, for me, the best reference with the source of information for that.
But it seems like a very recent paper. I would think that quantum graphs were older.
Yeah, but I'm saying that, I mean, you can think about generalized approaches, like you are not assuming some of them, right? And then you can
So this is probably some survey.
Yeah, this is like
Okay.
This is like a server, like a overview, a review of what is known basically in this. I mean, there are of course new results, but I mean, this is a very good source of information about what is known in this topic. So I recommend this one to look for the details and to see what you can do if you are like forgetting some of the axioms or whatever. Okay.
Sorry, it just reminds me, Mark, please correct me if I'm wrong, but I believe that you wrote a very beautiful survey paper about the irrational rotation C-star algebra, quantum torus, which gathered a lot of information. And it reads like a charm. Do I remember correctly that you wrote such a paper?
I certainly wrote a paper about the irrational rotation algebra. I'm not quite sure how you're viewing it as relevant here.
Okay. No, it's not reviewing it. It's just I think that it had a lot of information gathered together
Yeah, as a survey paper, yes.
Yeah, exactly, as a survey paper, and it just occurred to me that that's good analogy. Okay, sorry for the interruption.
Okay. So let me just continue. So yeah, so let me now present one of the main results.
Sorry, I have a question again.
Yep.
Sorry. In the case of classical graphs,
Yes.
is it sure that at least in this classical case, these two approaches coincide?
Yes, because I am giving you the corresponding operator subspace, and you can find the one-to-one correspondence actually by this map. Okay. So let me now go to the one of the main results. So the first one is to generalize the Mycielski transformation into the framework of quantum graphs. And what you have to do, so I mean, it's like quite natural what you have to do with the finite quantum space. You just take the straightforward analog of the previous construction, right? The quantum setting.
So direct sums of C-star.
Exactly. Yes. It's also quite, I mean, maybe not obvious. It's quite intuitive what should be the structure of the quantum adjacency operator in this case. But you have to be careful about the presence of deltas, where to put the unit, maybe the value of the psi on some element, whatever. So there are some subtleties here, and it has to be properly fit, but it's doable. And of course, you have to also define this map psi here. And yeah, as I said, it's not so counterintuitive how to do that, but you have to fix several parameters. And after that, you have to show.
Could you go back? Oh, yes. I'm a bit confused. Why don't you? That's the same thing. No, sorry. Sorry, it's x&y. Sorry.
No, it's x&y. Yeah.
So why not to write this new adjacency matrix in a block form from which you could compare it with the classic?
Yeah, exactly.
Well, yes, I mean, this is what we did, but the point is that I had not enough space here, so I decided to do it like that.
Okay.
I mean, it's just because of the lack of the space on it, and I didn't want to.
Yeah, like Fermat didn't write its proof. Yes, I know.
Yeah, I didn't want to goes outside the slide. So that's the only reason. Yeah.
Exactly like Fermat, yes.
Yeah. So okay. So let me now. Okay. So this is the Mycielski transformation. I mean the quantum Mycielski transformation is called this way. And now the generalized version, as you can guess, is almost the same thing. So you basically take R copies now of this quantum space. You generalize this map psi in a straightforward way, just adding more copies of this map here. And the structure of this A mu is, as you can expect from the classical situation. And I mean, saying that it looks quite natural, but actually, in order to show that this is a good construction, we need to play a bit with this. So let me introduce some notation. So let me denote by iota k the isometric embedding of the kth copy of L2 into the larger Hilbert space for this Mycielski transformation. And iota 0 denotes the isometric embedding of just functions on the distinguished point. And then this map A, the new one, can be written in this form. And for me, this form is more easy to work with, because you can easily see the structure. So basically here you see the nice symmetry, right? Between how these blocks are distributed in the huge matrix. And here you have this non-trivial part where we had to really fix all the coefficients properly to ensure that indeed this is a well-defined quantum graph. That for any r larger or equal to 1, of course, integers, the generalized Mycielskian constructed in this way is a quantum graph in the, for the definition of quantum graph I gave you before. So it satisfies all the axioms. So like the proof is quite straightforward, but requires a few pages of tedious computations, and you have to really play with all the maps and be sure that all the deltas and all the things are fixed correctly. Moreover, if the quantum graph G was irreflexive or reflexive, the new one is also of this sort. So this is a nice property, because as you remember, in the case of a Mycielski transformation, it was like that. So, and the irreflexivity was like a crucial part to prove the Mycielski theorem, right? Because the Mycielski theorem was only for irreflexive graphs. So this property is quite nice. Okay. So having said that, let me go to the study of characteristics of Mycielski transformation. So I will give you now the definition of quantum coloring, which is taken from this paper, and it is of course equivalent to the one you can define by using the quantum games, but for practical reasons, this version of the definition is more useful. So okay, let's consider the irreflexive quantum graph and the associated operator space defined through the map I gave you on one of the previous slides. And we are saying that this quantum graph possesses a quantum C coloring if there exists a finite for normal algebra N and a partition of unity in this algebra, such that for all indices A and all elements of this operator space S, we have this equality. And okay, that's the notion of C coloring. It might look suspicious, but if we now define two things, so if we now define the quantum chromatic number as the minimal number of C, such that there exists a C coloring, okay, this shouldn't be here because N is by definition finite, so just forget about this. And the local one is defined with N.
Sorry?
Yep.
So you mean the finiteness of the von Neumann algebra as what? Finite dimensional, or since there is a confusion, since there is a notion of finiteness in the context of von Neumann algebra,
okay,
in this context of Murray von Neumann order. So for
yeah,
example, type 2 factor is finite in the sense.
But in this case, it doesn't matter because at the very end, the definition of quantum chromatic and local, we are taking only finite dimensional things. So.
Okay, so finite dimensional von Neumann algebra is always finite in the sense, in the more general sense. Mm-hmm.
So this is what we are using. Yeah, exactly. Okay, so let me just.
I have a question. In your definition, you are considering two cases, dimension finite or dimension equal to 1. Why not to consider the condition dimension of n is equal to c squared?
Yes, that's another
Which would
possibility.
be the
Yeah,
most natural assumption in this context.
of course. I mean, that's true. Okay,
Mhm.
I don't have a good answer why not. Of course you can, but dimension 1 is because of this exercise here that if you take a classical graph, this is the same as the classical Hermatic number. This can be quite easily seen. The point is that in the quantum case, you can formulate the. I mean, I've shown you the definition of the quantum Hermatic number in terms of a quantum non-local games, and actually they are equivalent if you are having this kind of condition. So this is the quantum Hermatic number, which is equivalent to the one defined in terms of quantum non-local games, like the standard quantum Hermatic number, which is was defined before in the literature. But of course, one can.
Just another stupid question, if I may. Is it possible to have a quantum graph, properly quantum graph, non-classical quantum graph, we would still have this property that chi of g is equal to chi log of g?
Probably yes, but I don't have now an example.
Okay, okay.
I don't see a reason why not.
You don't see any red flag, okay, yeah, just,
Yes.
it's not important.
Okay, so that's the notion we would like to use here. So the notion of quantum Hermatic number and the local Hermatic number, and sometimes I will just say classical Hermatic number because it's basically the same thing for classical graph. So just to explain the language I'm using here. So what we have proven is that if I have an irreflexive quantum graph and any are at least 1, so any type of Mycielski transformation, then both quantum and local Hermatic numbers satisfy this inequality. So we don't have for free the equality like in the case of Mycielski theorem, but in the quantum setting, what we can show, at least what we can show, is the inequality between those two numbers. So there is a bound on this Hermatic number of this Mycielskian of quantum graph. And let me just give you a brief idea of the proof. So the first step, we reduce the problem to the local version. I will not give you the details how we did it, but basically that's the first step, the reduction to the local version. And the idea is that if we had a coloring of the original, like C coloring of the original quantum graph, we wanted to find the coloring of the larger one with one color more. And we did it by looking what was the original proof of Mycielski. So basically, you can see that in the original proof, the new coloring is defined by just coloring the distinguished vertex with a new color and leaving each copy of the original one with its original color. And we can mimic this kind of idea by defining those operators Qi in this way. And after that, we have to verify all the requirements about being C+1 coloring. So basically all the conditions I wrote here. So that's the idea of the proof. So it's like a straightforward way of somehow translating what was done in the classical case into the quantum world, and then verify if this kind of naive quantization of the proof indeed works. That's the idea. Yeah, okay, so that's the first result about the Hermatic number. And yeah, this is the comment I already mentioned, that if R is larger than 2, then the generalized Mycielskian in the classical case may leave the classical Hermatic number changes, and there are no examples for this. So we don't expect to have the quantum version of the Mycielski theorem in general also here, because already for the classical graphs, it doesn't work. But so what happened in the case of R equal 2? So the one for which the classical Mycielski theorem is, the original Mycielski theorem was proved. So let us now take the C prime plus 1 coloring of the Mycielskian of a quantum graph. And then one can show that without loss of generality, we can parameterize this coloring in this way. So we have now basically 6 operators. One is 0, the other is 1. And we can show that all the actions of being C coloring, C prime plus 1 coloring implies that P02 is 0. So we have a simplified system of operators. And we can show that if this C plus 1 coloring is such that not only this will fit that P2 is 0, but in addition, this kind of commutativity relation holds, then the local chromatic number of a quantum graph is the smaller by 1 than the local chromatic number of the Mycielski. So the Mycielski theorem holds under this weird additional assumption, and we don't believe that this assumption is satisfied in general. So we don't have a concrete counterexample of a quantum graph that have the same local chromatic number of a Mycielski of the same as the local chromatic number of the original graph, but because of this kind of weird property that appear here, we don't believe that the Mycielski transformation is true in general in the quantum setting. But what is known as
so this proposition is not in the spirit of Mycielski theorem. It's what is happening under demycielskification of.
Yes, exactly. Yes. So I mean, we're trying to see if we can do something similar in the quantum setting as he did in the classical one, and we found that actually it seems okay. It's not the statement that it cannot be done. It's a statement that it seems like there's something that we cannot do here, and this is, I mean, this is exactly what I'm saying. This is what we cannot do. So if we have this kind of condition, then we can proceed, but we cannot like avoid this. I mean, in general, and we are not saying that in general it's not possible to show that it's not doable, but it seems weird that it is possible. I mean.
I have a question again. What about the case when instead of local chromatic number, you are considering quantum chromatic number?
This is the next slide, I think, or the other one. So the quantum one is the answer for the quantum one is no. For the local one,
okay.
So, I mean, I think this is like the next slide or next one. Okay.
So for quantum chromatic number, also this is not true.
Yes. So
Can
let
be
me
not
go.
true.
Yes. So let me just go to this, but before that, let me just mention the other inequality. So I mean, I have shown you the one with the upper bound. So now we have the lower bound for the Mycielski of this. I mean, chromatic number of the Mycielski is not surprising, but yeah, we have this lower bound also. And now there's this comment I wanted to make, that for the classical graph, there exists an example of a concrete graph for which the Mycielski of this graph, even the classical graph, for which the Mycielski of this graph has the same quantum chromatic number as the original graph G. And this is this famous G13 example from the paper by David Robertson and Mycielski. And as I said, we don't.
Is it Robertson or Robertson?
I think I pronounced this correctly here. I mean, it's exactly as I wrote here. I think so. Maybe I have to check the email from him I got about it. Okay, so I think it's this.
Because is it the same guy who wrote the paper with Wojtek Szymański? There is a nice fallback theorem by Robertson Szymański.
Okay, that I cannot show. I don't know. I don't know the paper.
I mean, he was an Australian student of Wojtek Szymański.
Okay,
Of course, I mean, it might be a different person, but
What about initials?
I don't remember initials. No, I don't.
Yeah, I also don't. I know what you are talking about, because that two people of the same first name and the last name, but I'm not sure about the second initial E.
Okay.
Okay, so I'm referring exactly to the person who wrote the paper with Laura Marcinska in 2016 about this G13 graph. Okay, so I think that this is the only answer I can give about this.
Correct.
Okay, thank you.
Okay.
That's a different person. Okay, it has been settled.
Okay, yeah. Okay, so this is the example of, I mean, a counter example for the quantum chromatic number. but still we don't know. Okay, we know that for the classical graphs, we cannot have the equality here. It's always bigger than 1, but maybe there exists a purely quantum graph for which the Mycielski transformation doesn't work for the classical chromatic number. So this question is still open, and we still don't have a intuition how to find such an example. Okay, fine. So this is about the chromatic number. So now let me jump to the second characteristic, because I mean the Mycielski transformation not only changes the chromatic number in a specific way, but also didn't produce any triangle inside the graph. So now we would like to consider the clique number for the quantum graphs. So first, let me just give you remind the definition about the clique number for the classical graph. So the size of the largest complete graph containing the graph. And there's an equivalent way of characterizing this number. And this was shown in this paper here, that you can look at the cardinality of the set, the largest cardinality of the set of vectors, non-zero vectors, such that for I different than j, those dark ket vea belongs to the operator system associated to the graph. And it was shown that this is equivalent definition of a clique number.
And complete means that between any two different vertices there is an edge, right?
Could you repeat the question?
Complete means that between any two distinct vertices of your graph there is an edge.
Exactly.
Right?
Yes.
Okay.
And this definition actually is quite easy to generalize for the quantum graph, and it was also proposed in this paper. But basically, you are replacing the vector. You are just taking the vectors from L2, and the system here is now the operator system for the quantum graph. So it's like a straightforward way. So this way of presenting the clique number has a straightforward way of to be generalized to quantum setting. That's the okay. So
sorry, I have a question.
Yep.
In your definition of quantum chromatic number, you allowed tensoring with finite dimensional von Neumann algebra.
Correct.
Here you are taking this lemma, this classical lemma for the classical graph, as a definition for this clique number for a quantum graph.
Yes, and I think this is the answer. It's answered here.
Why you assume that
I think it's here. I think
it could be called local.
no. I think it's exactly answered here. The answer for your question is exactly written right now. That you can show that this definition is equivalent of taking the maximal size of a complete graph that can be embedded. Into a quantum graph in this following sense, that the morphism between the quantum graph is defined in this way. So there is a Hilbert space H and an isometry between L2F1 into L2F2 tensor H, such that you map the one operator system into the other one. So you can find an equivalent way of defining the clique number by saying that there's the maximal size of a graph that can be embedded on, so it's included in this graph G. So, but it means that you have to define what this arrow means. Okay.
Okay, so it's a beautiful result. Yes. That explains it.
And there are also some variations about that. Basically, you can define some quantum versions of those numbers where you are not considering the classical homomorphism, but by quantum homomorphism of quantum graphs. And these types of notions were also discussed. I'm not going to do it here, but just want to mention that you can also think about this type of generalization, okay, that you are replacing this morphism by the quantum morphism. And this also can be done. Okay. So having said that, let me just say what is the main result about the quantum, about the chromatic, so about the clique number for quantum graph and the Mycielski transformation. So the result is that, of course, the Mycielski transformation doesn't change it, and the same is true for all the generalized Mycielskis, as expected. So at least we know that the generalized Mycielski transformation doesn't change the clique number in this sense, and we know that in some cases it might not enlarge the chromatic number by 1, but at least it cannot enlarge by more than 1. So we have the upper bound for the chromatic number. Okay, so far so good.
So do you assume, even before going to quantum, do you assume that the graphs are finite, meaning that the sets?
Yes, exactly. Finite dimension, everything is finite. Yes. In the context of Weaver's quantum graph, I can think about the infinite dimensional cases, but it's more subtle. But he defined the infinite dimensional cases also, and it's also, I mean, something about the infinite dimensional quantum graphs, of course, is known, and I mean, we have some, and there are some kind of results you can find, but yeah, for simplicity here, I am assuming finiteness only, just to avoid any technicality, just to see the structure first. Maybe the next step is, of course, to look at the infinite dimensional cases, but let's first see what we can learn from finite one.
I had this question because I was wondering whether you could take your R being equal to infinity, whether you can have like an infinite
Well,
version.
this is what, okay, I didn't think about the limits, like, but yeah, it's a good, but I mean, for any R, does it change? Okay, I expect, okay, let me not comment about that because I don't know the answers. I just wanted to speculate here. And I expect it's the same, but it's not different. Okay, so now let me go to the last part of my talk, and I would like to discuss the symmetries of graphs, quantum graphs, and how the Mycielski transformation affects the symmetries. So let me just remind you that, okay, what is the classical symmetry of classical graph? So basically we're permuting the vertices such that we don't change the connection between them, right? So if there was an edge, there is an edge after the permutation. The permutation basically...
Sorry. So by classical objects, you mean finite combinatorial objects?
Yes.
Yeah.
Well, I didn't get to this point, but yes,
Otherwise, you can have symmetries of like Lie groups or something.
Yeah, of course, yeah. I'm talking about the finite sets only. Everything is finite.
And discrete.
Yeah, that's another point. Okay, so if I have a classical graph, the permutation of vertices is basically 0-1 matrix, right? And the entries have to satisfy some rules. And instead of looking at the permutation, I can look at the permutation, I can look at the functions over the set of permutations, and we know how to characterize the set. So basically, there's a set of all, I mean, there's a C-star algebra generated by all Pi j such that universal C-star algebra generated by all Pi j such that those conditions are satisfied. And I mean, if you now follow the logic by one, you can forget about the last condition and have the quantum permutation. So we are not assuming commutativity of the entities. But basically, that's the idea behind quantum permutations. I mean, those concepts are, of course, well known. I'm just summarizing it here because I will use some of them in the next slides. And yeah, the main idea is, as I said, that the quantum symmetries of classical finite discrete objects are just quantum permutations satisfying some additional conditions like commutativity condition, quantum adjacency matrix, understood the proper way, and so on and so forth. And this leads, of course, to the concept of quantum groups for those quantum symmetries. And this is like, I mean, standards, let's say, not textbook material, but almost. But let me just give you some remark how it works in practice. So suppose that I have a finite set n, and okay, I have the basis of this algebra. So how I can write the action? Basically, I can encode it in this way. Those u, I, j are now appearing here on the second leg of my tensor product, and this kind of action preserves the uniform measure on X. So like, I mean, nothing unusual, just a standard way of saying what is the action of quantum symmetries on a finite set. But this kind of picture now can be generalized, and it was done in this paper 2022, that if I have a quantum graph, the quantum symmetry group is the compact quantum group equipped with an action that preserves the measure. I mean, preserves this function psi in this case. So it's given by this formula, this action. And this action is assumed to be universal among all compact, I mean, the pair of compact quantum group, and the action is the universal among all compact quantum group actions preserving this map psi, such that it commutes with the quantum adjacency matrix in this sense. So it's like a straightforward generalization into the quantum world of what we know about the classical graphs and the quantum symmetries of classical graphs. And moreover, I mean, it's quite easy to see that if you have an orthonormal basis in L2, it determines a unitary matrix U by this formula here, and the C-star algebra C out G is generated by the entities of this matrix. So this is like a standard.
Sorry, is it obvious that this quantum symmetry group exists?
Mm,
It's a
that's a
theorem.
good-
It's a theory.
Not obvious, not obvious.
not obvious, but yes.
Not obvious.
Because it's kind of funny, you give a definition, so.
It's a theorem of one.
Yeah.
Yeah.
Exactly.
Plus
so-
one, because there are about 1 million ones.
So
In
okay.
this context, it's only one. One.
Yeah, so this is basically the notion of quantum symmetry that we would like to use to say about symmetries of quantum graphs. And yeah, what we can say about the Mycielski in this context. So let's start with some quantum graph. I think it should be irreflexive to fit our construction. I didn't mention it here, but it's irreflexive. And then for any R, we define this weird map here. And okay, it's you can think of it like okay, it looks complicated, but basically it's just if you look at it, how it is defined, you just see that you just somehow embed the action in the proper place in the larger space, on the larger algebra, right? So basically we are having the original action here, and you just embed it into the larger algebra with direct sum of those copies of CG. And you are showing that you can show that this map is a unitary star homomorphism that, yeah, it's compatible with all the structures basically. And having said that, it means that the compact quantum group of the original quantum graph embeds as a closed subgroup of this compact quantum group for this Mycielski of this quantum group. So this is the result here. So we know something about the relations between the quantum symmetries of the original graph and the Mycielski. Of course, it's not all we want to know, but that's the first step. And the second thing we want to know is that if the quantum, the Mycielski transformation preserves the quantum isomorphism between the quantum graphs. I mean, it's quite natural, but do we know that? So first, let me just give you, I mean, again, definition from the paper I mentioned in the previous slide, that the two quantum graphs are said to be quantum isomorphic if the corresponding quantum groups are monoidal equivalent. So there's a definition of quantum isomorphism between two quantum graphs. Quantum graphs are set quantum groups at the very beginning. So two quantum graphs are quantum isomorphic if the corresponding quantum groups are monoidal equivalent. And what we can show is that if we have...
Sorry, can you remind me of how you define that this monoidal equivalence of quantum groups? So two quantum groups are monoidal equivalent if and only if what?
Oh, I wanted to okay.
Please give me the gist. I don't remember the definition.
Categories
Category representation.
monoidal equivalent.
Okay.
So it's a strange definition. Quantum isomorphic should be called quantum equivalent.
Okay.
What isomorphism is meaning here?
Okay. In this paper, they had several notions of quantum isomorphism, I think, and they can show that they are equivalent to this one. So it's like, I mean, we are choosing this definition as the definition of being quantum isomorphic, but like the origin is that there was a different definition of being quantum isomorphic, which is equivalent to saying that those groups are monoidal equivalent. But
because from the Planckian point of view, it is not enough to have the monoidal category representations of this quantum group. You need to have these groups to be isomorphic, you need this neutralizing functor, forgetful functor to vector spaces. If you are losing this requirement, you are obtaining something which could be called, I don't know, monoidal Morita equivalence, something like this.
Okay.
So calling it isomorphism with some quantum decoration is not right.
Okay,
Right.
but as I said, I just took the definition from this paper. So
Yeah, okay.
okay, so this is the thing that we are using from someone else, and I'm not going to discuss if okay. As I said, the history that there was a different definition of quantum isomorphism, which turned out to be equivalent to this one. That's the only thing I can say about the origin of this notion, this context. Okay, but what we can say about our problem? So suppose we had the two quantum graphs, R and G, and suppose they were quantum isomorphic in this sense, then it's a quite straightforward application of some basic properties of monoidal equivalent, that the deltas which appear in the definition of delta phones must be the same. So basically the same value of delta must be for those two graphs. And this follows some monoidal equivalence. And it means in particular that, so okay, having that the deltas are the same, we can show that the Mycielskians are also quantum isomorphic in this sense. So yeah, basically something that we expected, that if the two graphs were quantum isomorphic, the Mycielski transformation shouldn't change this property.
And this is implication only one way, or is the reverse implication also true?
That's a good question, and I don't have a proof right now. I will think about that, but as far as I remember, we didn't finish this part.
Okay.
It's like, so that, okay, I should mention that the part about the quantum symmetry is still the ongoing work. So there's still a lot of things that have to be finished. So I'm just saying what we have so far. So far we have those two notions, two propositions about this. I mean, several others, but like the two.
So it's a question about the converse for R equal to 0.
Yeah.
Yeah, exactly. Okay, so having said that, let me just, okay, so as I said, we would like to understand the quantum symmetries of the Mycielski transformation in the quantum setting. So let's see what we know from the classical version. So for that, let me define the twins for vertices in the classical graph. So I mean, we say that two vertices are twins or twin vertices if they have exactly the same neighborhood in the graph. Okay, so that's the notion and that one can introduce. And in 2019, in this paper, there was a nice observation, proposition that if the graph is twin-free, then every automorphism of its Mycielski that fixes this distinguished point is induced by an automorphism of the original graph. So this is something that is known about the classical Mycielskians, and the proof can be summarized in those 4 steps. So basically, the first step you are just parameterizing any automorphism that fixes the distinguished point. And basically, you can show that it is of this form, where those two, ρ1 and ρ2 are automorphisms of the original graph, such that they satisfy this relation, so that ρ1 composed with the adjacency matrix of the original graph the same as ρ2 of times AG. But this actually implies that if you look what does it mean in practice, if you evaluate this on a given vertex, for example, it means that the characteristic function of the vertex, of a neighborhood of a vertex V, is mapped by ρ1 into the same as ρ2, so it should be ρ2 here. So basically, ρ2 composed of the characteristic function of the neighborhood of V is the same as ρ2 composed of the characteristic function of NV.
I think in your definition, sorry, but I have to point this out. In your definition of twins, I think you are missing that X should be distinct from Y.
Of course, yes, of course. Yeah, right. Otherwise, it's like an empty statement. Yeah. Okay. So we have this step, and now since we know that the automorphism of a graph is just basically some permutation of vertices, this object, so ρi composed of chi n v is basically some characteristic function of a new vertex. Let's call it sigma I of v, where sigma now is the permutation of vertices, right? And the lack of twins in this condition means that sigmas must be the same, so rho must be the same. So it means that we have the proof of the proposition. So this is the summary of the proof they proposed in this paper, phrased in a way that now we can use in the quantum setting. So this motivates us to introduce the notion of quantum twins. So suppose we have a quantum graph G and H some quantum group, and we say that G has H twins if there exists a pair of different actions of G on H, ρ1 and ρ2, such that
Not G on H, H on G.
H on G.
And you said G on H.
okay,
You
yes.
wrote it correctly, you said it incorrect.
Okay, yeah, too many letters. Yeah, of course. Actions of H on G. Yes. I mean, for me, G is always a group, so I have to somehow
Yeah.
think what I am saying. Yeah. So this is the definition of quantum twins, and now we say that G has a quantum twins if there exists a quantum. I mean, if it has H twins for some quantum group H, basically. So we are not specifying this H. And if the above group H is now classical group, then we say that the quantum graph G has classical twins. And of course, if it's a kind of lemma or proposition that we proven that if you take G, the classical graph, then the notion of classical twins coincides with the classical notion of twins introduced.
Sorry, is it obvious? I'm trying to see.
No, it's not. It requires some work, but
Okay.
it can be shown that it is the same.
But you're over time.
Yeah, that's the reason that I'm not giving the details here. Just trying to go to the final slide. So the theorem that we can prove about the Mycielski then is that if G as a quantum graph does not have quantum twins, and the quantum action fixes in this additional point, then we have the isomorphism between the quantum group of automorphisms of those two graphs, quantum graphs. So this is what we can show about the Mycielski.
Sorry, so probably for classical twins of a quantum graph, the same holds, or not?
Yes, of course. Yes.
Okay, so this is the motivation for this.
Yes, that was the motivation of introducing this notion of quantum twin, because we wanted to have something similar like in the classical case, and we replace the original proof in a way that can be easily generalized to quantum. And this is the notion of quantum twin proposed. And now we are studying the quantum twins by itself. So there's a natural question one can ask: does there exist a classical graph that has no classical twin vertices but has quantum ones? So are the two notions for quantum graphs the same or not? And as far as we know, for now, we have checked by explicit computations using some tables of known graphs with graphs with known quantum symmetries, that for all graphs with at the most 6 vertices, there's no distinction between those two concepts. So there's no graph with at most 6 vertices that has classical twins, but that has, that for which the classical notion of twin is the same as the quantum. So always for at most 6 vertices, there's no difference. And the idea of the proof was just checking some necessary conditions, like, what does it mean to have when we can expect to have quantum twins? So we have to have some quantum symmetry, non-trivial one, we have to have singularity and adjacency matrix, and so on and so forth. And then we use those properties to reduce the number of possible candidates, and then we check one by one all the remaining possibilities. And we know that for graphs with at most 6 vertices, there is no for which those two things are different. Moreover, for the
sorry, couldn't be these two potential candidates tested using computers?
You are referring to the second part. Yes, this is exactly what I was trying to say now, that now we are looking at the vertex transitive graphs with at most 13 vertices. And there are 2 candidates, exactly. One of them of 10, the other one of 12 vertices. And we are trying to do this now on the computer. There are some issues because, I mean, I can cite, for example, that, okay, so we know what are the quantum symmetries of those graphs. And basically, our previous tools to show that we don't have this quantum twins here was that we were using the so-called Fulton criterion to reduce the matrix that represents the potential candidates for the representations. In this case, it's like an empty statement, so we cannot use the tools we use for the graphs with at most 6 vertices. So it's a quite complicated problem. I mean, it's doable, of course, but at this moment we don't have the full answer. I mean, we've got some mess from the computation on the computer, so we are trying to understand how to do it better without like asking the computer to solve by brute force all the equations we have. So I mean, we are working on this. So this is like the work in progress actually right now, exactly trying to understand if those 2 candidates are indeed good candidates, or also for them there's no way of having quantum vertices. Okay.
Can you estimate the complexity of this problem?
At this moment,
Computational
no.
complexity of this problem? Okay.
At this moment, no. I don't know that.
No, it's not.
No, it's. I mean, I didn't think about this, so I don't know. But yeah, I mean, so for this one, I mean, this straightforward way of doing that, if we have the Fulton criterion, it's easy, relatively easy, because basically you have to check that, okay, no classical twins means no 2 rows in the adjacent symmetries which are the same. Presence of quantum symmetries, okay, there are a list of known graphs with quantum symmetries, and we are using them. So we are not doing new things here. And then the next thing is that, I mean, we have this equality, so we want to have this guy to be singular. Otherwise, it's a trivial statement. The 1 is equal to 2. So there are some checks that you can do on the computer, and that is just linear algebra, so it's easy. But there are some steps that require some more sophisticated thinking, and we are still trying to do this for those 2 examples because they are like quite huge matrices, and we don't know how to. I mean, we don't know the result yet, so this is still running on the computer. I don't know how to do this.
And what does mean vertex transitive?
Okay, I expected this question. So now, and now I forgot the answer. Okay, so let me think if I can get it from the top of my head. All right, now, so vertex transitive, I think it was that.
Because the graph is already connected, right? We understand.
Yes, the graph is always connected.
Yes.
Okay. I forget the. Okay, maybe later I can send you the reference where this is, because I have it exactly on my computer right now, but I cannot open it.
Do you have an idea what it should be?
It should be
I can
connected.
check this.
So connected is already mentioned. Connected
No, this is
vertex
something else.
transitive.
So I don't understand.
That's why I'm asking this question.
Just a second. No, okay, sorry. Okay, yes, I have. So the vertex connect. Okay, so the transitivity is about the automorphism. So basically, you are saying that
Okay.
you can connect by automorphism. Okay?
So symmetries act
Yes,
transitively
exactly.
on this graph. So it's not about graph itself. It's about symmetries.
Well, it's also about the graph because it's a symmetry group, quantum.
It's not a dynamic of the paths.
Yeah,
It's the dynamics of the symmetries of the graph.
obviously.
Yeah, exactly.
Dynamics
So
of-
it's like a different type of connectivity. So we have like graphs which just connected in 2 different ways. Okay.
Perfect. Yeah, thank you so much. Yes, perfect.
So that's actually all I wanted to say, and I just have a summary of some open questions. So as I said, we are looking still for an example of quantum graph. Yes, this is the trivial story. It should be mu of G, of course, here. Otherwise, it's a quite trivial statement. So quantum graph for which the local thematic number is the same as Mycielski. And the other one is to look at different type of clique numbers. So for example, you can define quantum clique number by considering now the maximal cardinality of the size of quantum complete graphs, which are defined. I don't want to go to details, but you can define the notion of a quantum complete graph, and you can study this type of objects. And how it is affected by the Mycielski transformation. We know something about the inequalities right now. We still don't have a full answer for equality. And the last question is about the existence of a classical graph that has no twin vertices, but has some quantum one. So we would like to understand if the notion of quantum twin is different than the notion of classical twin. Okay, so that's basically all I have.
Thank you so much. Okay, so the speaker has already asked us his questions. Now it's our turn to ask him our questions. Who wants to begin? Adam?
No, I was just clapping my hands actually, and also. No, but I don't have any questions.
Okay, and
I can answer your question.
okay,
What is my understanding of vertex transitive?
okay,
Okay,
yes,
in classical topology geometry, such a situation is called homogeneity.
yes.
So it is vertex homogeneous.
Okay,
Okay, if symmetries is if the action of symmetries act transitively, then this such an object is called homogeneous always. Okay. But if you speak about graph, which is vertex transitive, it is not clear with respect to which dynamics.
yeah, but,
Right.
yeah.
Actually, there's a quite famous conjecture by Lover that if you have a connected, of course, finite vertex transitive graph, then it must contain Hamiltonian path. And I think it's still open. That every vertex transitive graph connected contains Hamiltonian path.
For instance, it's a Hamiltonian path is some kind of dynamics.
Yeah, but I mean, I think it's still open if this is no or not.
Okay, any other questions? Zoom or room? I don't see anybody on Zoom. Raising hands. Anybody in the room? Sound like we are done? I'm done. Okay, so let me wind it up by asking you about some examples. I mean, you gave us only one K2 example throughout the entire talk. So what I'm missing really very badly from your talk is, say, an example, a simple-minded example of a quantum graph, of a quantum Mycielski transformation, an example of a quantum twin, you know, something concrete I could hang my mind. It's completely missing in your talk.
Yeah, so for the last question about the quantum twin, we don't know because all the things
No,
checked.
but I mean, can you just show any graph with a quantum twin? Tell me that's a quantum graph, it's quantum twin.
Yeah, but the problem is that the quantum twins are the same as classical ones for the small number of vertices. We don't have any example which has quantum but no classical.
Okay.
So we don't know how
Okay.
to find the example. So this is a question still.
Okay, so
The picture would be very complicated.
okay, I've got it. But say a quantum Mycielski transformation of a quantum graph. So the simplest non-classical quantum graph. With a quantum
Okay.
Mycielski transformation.
What are non-classical simplest quantum examples?
Exactly, with this,
Okay,
all the quantum stuff that you did. This is what I very
I see
badly.
your point. Okay, yeah. Okay, I don't have an example right now to give you the concrete description, but I mean, you can take, I mean, the easiest one I would say is the quantum complete graph of two vertices. And but this is like a trivial one because I mean, basically the adjacency matrix is like an identity operator. So I mean, you just insert the identity blocks in this matrix, so it's like quite trivial thing. And the non-trivial one, well, I don't see how to easily present them, to be honest. The problem is that this is always about the dimensionality and how to draw the pictures here. The trivial ones are too trivial to show something non-trivial, unfortunately.
Okay,
Maybe I have a question.
all right, go ahead.
A question about constructing this non-classical minimal quantum examples. If you, for instance, if you start from matrix arguments,
Mhm.
then you can describe combinatories of mappings between them in terms of Bratelli diagrams.
Correct.
Do they play a role in this theory? Because
That's a
Bratelli
good
diagrams
point.
this is non-classical behavior of something which is a non-commutative counterpart of something finite, that simply finite combinatories. Okay,
Mhm.
but they are still non-trivial because you have this
Yeah, I
blocks,
understand.
matrix blocks which can be mapped one to each other by non-trivial maps. So I wonder if this non-triviality of Bratelli diagrams could play a role in this theory.
Okay, the short answer is I don't know, but I would like to look at this because I didn't think about this in this direction, so I don't have any comment about that. Yeah.
It would be like secondary combinatories
Mhm. Yeah, I understand.
because Bratelli diagrams, it's a kind of combinatories, but of secondary level. Okay.
That's true.
So
Okay,
it's a
yeah.
parallel to the idea of secondary topology. For instance, if you have topological spaces or some geometric spaces, you can speak about moduli spaces of some objects living on these spaces. Okay, and then you can study topology of these moduli spaces. So it's like secondary topology. So in this case, it would be like analogical secondary combinatorics.
I see. Okay, it's a good point. I don't know. I have to look at this. It's quite interesting. Yeah.
Okay.
Okay, so in this case, let us thank our speaker again. Thank you so much. So we adjourn now and we stop the recording.